In this presentation, I want to talk about the random walk and use some practical problems to induce the recurrent and transient properties of random walk. Random walk is known as a discrete stochastic process, which describes a path consisting of a number of random steps under a mathematical space. It has many practical applications in physics, biology, and finance. A Brownian motion is a continuous analog of two-dimensional random walk, and there is a deep connection between the Brownian motion and random walk. Here is a picture of the one-dimensional random walk. Here, the definition of random walk. Random walk tell us for x, which is a random variable, Sn is a random sequence, always can be written as Sn is equal to Sn minus 1, which is a previous term plus the random variable Xn. So we always use Sn to denote as the distance in the random walk. So Sn also can be written as the z plus x1 plus 2xn, where z is also always denoted as the original point or original position. For a simple random walk, uh, the characteristic of the simple random walk is that for each xn, it only has two values, either -1 or +1. And for the original position, S0 is equal to Z is always equal to 0. So for a simple symmetric random walk, we denote each probability for each choice is the same. So in the one dimension, the probability will be 1/2. Here is a practical problems. Consider a drunk person randomly walk along a street. Uh, what is the possibility for him to come back to the origin? So this is actually a one-dimensional symmetrical simple random walk. To calculate the possibility for backing to the origin, we can build a table of possibility with the steps we denote as n and the distance, what we have already explained as a random sequence Sn. As you can see from the table here, for each steps is a column and the distance is a row. So for whenever step n is equal to odd, like 1 to 3, the possibility for backing to the original point is always 0. So only when n is a even number, when n is equal to 2k, we can find the possibility for backing to the origin. So assume the capitalized N is the number of passes to the origin. We have the possibility for backing to the origin is equal to capitalized N divide the total pass, which is 2 to the power N in the two dimension. We can also write as a binomial coefficient form. So the starting formula is a good approximation for the factorials, which we can write the factorials as a algebraic way. So here the epsilon is a small number, and as n goes to infinity, epsilon n will go to 0. So we can rewrite the p, the form of the probability as the this form, and as you see, the n is equal to 2k, so n factorial can be also as n factorial divide the k factorial times k factorial. And we substitute by the starting formula, we can get a long expression of this form. So as you see, here is 1 plus epsilon n and 1 plus epsilon k. After simplify, we get this formula. Then our goal is to see when n goes to the infinity, will the sum of the possibility be converge or diverge. So in this case, when n is goes to infinity, k also goes to infinity. So we can see the epsilon n and epsilon k will eventually go to 0. So for this term, it's eventually will be 1. So we can make a close approximation of this term will be like this. And also the square root of pi is a constant, over 1 is a constant. So we can just take it out from the sum. And we see this part is what we have already learned from the math 2b, and this 1/2 is less than 1. So by the p-series test, we know this is diverge eventually. So the sum of the probability will be diverge, will be infinite. So one-dimensional simple random walk is recurrent, which means the drink people can find their way home for infinite times if they, as long as they walk around. How about the two dimension? As we see, for the two dimension, we have 4 directions for each step. So the possibility will not be 1/2, but become the 1/4. So as a similar from the previous one, we can know the number of the total paths for 2n steps becomes the 4 to the power of 2n. We also denote the capitalized n as a total path. So here is a formula we can write. And the k is steps to the left. As you know, if you want to go to origin, the two opposite directions step, the number of two opposite directions should be the same. So we denote the left as k and also the right as k, and therefore the steps go up will be n minus k and go down will be also be n minus k. So we can get this form, and we know the possibility is capitalized n divide the total number. So here we get the by the simplification we can get this form, and using the Stirling formula, we can get a form of the pi times n over 1 eventually. So as n goes to infinity, we can see this time the sum will like we take out the pi over 1 and see this is a harmonic series test we can use to get it also is divergent. So which means it will goes to infinity, which means the sum of the probability will go to infinity as well. So the two-dimensional random walk is also recurrent, and the drink people will they can find their way for home for infinite times as long as they run around or walk around a plan. How about the transient for the three dimension? Uh, as you see, we assume a bird flies through a three dimension, and each time it has 6 choices. So if we assume there are 2n steps, so the total path will be 6 to the power of 2n. The calculation steps are similar as the previous, but like the calculation process will be much more difficult because the binomial has we exist like 6 directions, so at least 3 variants. So here we calculate we just directly give the result of the sum of p, which you can see by the p-series test is is convergent to a constant which is less than infinity. So we deduce that the symmetric simple random walk has a transient property in 3D space, which means the drunk bird cannot infinitely come back to the origin. It will not come back anymore at a certain time. So here we use these strategies And thank you for you listening my presentation.